Okay, so hopefully people can hear me okay. So today what I'd like to do is finish off talking about near-term quantum algorithms, what I was planning to discuss yesterday, and then go on to talk about longer-term quantum algorithms for optimization and constraint satisfaction problems, in this sort of fault-tolerant regime that we have in the future. But first I'd like to sort of continue on, I guess, from Barbara's fantastic lectures by saying a little bit about what we can do to deal with errors in this sort of NISQ regime where we can't yet implement full fault tolerance, we can't implement these error correction protocols that have perhaps fairly large overheads, but we would nevertheless like to reduce the errors that we have in our quantum algorithms. And one way we can do this is via this notion of quantum error mitigation. So this has now become like a very sort of flourishing field with many sort of really interesting ideas being developed. I'm only going to very briefly say a little bit about a few of these. If you'd like to learn more, the survey paper I mentioned yesterday about NISQ algorithms is a nice place to start and goes through a lot of these different ideas. Okay, so the sort of overall picture that we have in mind is that we have a quantum circuit that's producing some quantum state rho, which ideally is some pure state corresponding to some interesting thing we want to do, like maybe it's the ground state of some quantum Hamiltonian or something like that. And we want to do some measurement on this, and we want to get some answer from that. And because the quantum circuit is noisy, we don't get a very accurate answer. We wouldn't if we didn't do anything, if we just executed it sort of naively. But what we'd like to do is come up with some method which somehow undoes this error and gives us something which better approximates trace of A times by rho, where A is the sort of observable that we want to measure. So I'm going to just describe a few methods which we can try to use to do this. And one of these, which I guess goes back to some of the earliest implementations of variational quantum algorithms, is so-called zero noise extrapolation, which is a nice idea, which is that we might think that in our quantum hardware, we actually have some ability to sort of vary the level of noise. We can't sort of decrease it below some floor based on the errors in our gates, but we might be able to increase it. Like, for example, we could just do everything a bit more slowly so that we experience more decoherence, or we could do something like, okay, instead of having a gate U that we implement, we could do U dagger U, which should just give us U if we have perfect gates, but as the gates are imperfect, we're going to get some kind of errors. And if we do sort of more iterations of that, we're going to get more and more errors. So this sort of idea allows us to turn up the level of error in a quantum circuit. And this means that we can compute some approximations to this measurement result, A, with different noise rates. And this gives us some kind of curve, because you would expect that as the noise rate goes up, this value A is going to head towards the value that we would get, say, if we had the maximally mixed state instead of rho, for example. So we get some sort of increasingly noisy results. And once we've got this curve, the idea is that we can go the other direction, and we can extrapolate this curve to see what we would have got if we had no noise at all. Okay. And this is a nice idea. Making it work involves, a bit of thought, because there's a lot of questions that sort of remain unanswered, like, how do we actually do this extrapolation? What's the right sort of fit to do to this curve? Are we getting accurate enough measurement results that we can actually do something better using this approach? So, making this work is not straightforward, but nevertheless it has been done, and in some cases has shown some improvements on just having the original noisy result. Another idea from the same paper from IBM is so-called probabilistic error cancellation. And here we imagine that we have some quantum circuit that we want to execute. We know what it is, but we also know that we have some sort of, we have a noisy process that's replacing this sort of real quantum circuit, right? And we assume that we know what this noise is. And like, for example, we might have a quantum gate that's happening, and then we have some depolarizing noise happening after that quantum gate. And so, this quantum circuit is like a mixture of the original circuit with, Pauli X, Pauli Y, or Pauli Z, perhaps after that gate. And once we know this sort of representation, so we could say, okay, well, imagine if we change the quantum circuit a bit, maybe by putting different gates in sort of around this sort of noise that's happening, then we have the ability to perhaps represent the circuit that we wanted to do as a linear combination of different circuits that are the ones we get when we have this sort of noise applied to it. So, you know, say the circuit we want to implement is C. Well, if we have the noise, we get like C tilde, like some noisy version of C. But you know, by changing the circuit in different ways, we can produce a family of noisy circuits like C tilde 1, C tilde 2, whatever. And we can then say, okay, well, hopefully the circuit we actually wanted to do, C, is expressible as a linear combination of these circuits, C tilde 1, C tilde 2. And by sort of running these different circuits and sort of summing up the results with some weights, this hopefully allows us to approximate the circuit that we wanted. So again, you know, one has to actually do the experiment to see if this works well in practice, even if it does seem to work well in theory. And it turns out that this can also indeed be useful, at least for sort of small-scale error mitigation. Another nice idea is called virtual distillation. Here, this is a more recent one. Here the idea is that we have some noisy state that's produced at the end of our quantum circuit, and we want to somehow purify this to get the actual state, right, that we wanted at the end. So we assume that the states that we have at the end is perhaps a mixture of a pure state with some sort of random noise, maybe. And we want to go from that sort of noisy version of the pure state to the pure state itself. And what you can do is you can produce a number of copies of this noisy state and do some kind of, something that looks like the projection onto the symmetric subspace, basically, to basically give you something which is sort of an nth power of the state that you started with, and which is obviously not, you know, a quantum state itself. You have to sort of normalize it. But what you can do is, using this method of having sort of multiple copies and doing a sort of projection onto the symmetric subspace, you can compute something which is like the measurement results of, you know, measuring A on this sort of m-fold power of the original state rho. Then you sort of normalize it by the trace of that thing. But the point is that as the number of copies increases, then this thing should head towards what you would get if you measured A on the sort of pure state, which is the dominant part of this noisy state, rho tilde. So this somehow enables you to effectively purify the state that you started with if you have many copies of it, at the cost of having some sort of overhead that scales sort of exponentially with the number of copies and then the number of times you need to run it. Okay. Another nice sort of family of ideas is one that I've called error mitigation by training here. So the idea here is that we might have some family of quantum circuits which we can actually simulate classically. So for example, Clifford circuits are an example of this. We know how to simulate these things efficiently classically, even though they can be kind of complicated and produce lots of entanglement. Another example is so-called fermionic linear optic circuits. It's like time evolution according to quadratic fermionic Hamiltonians. And these circuits, because they can be simulated classically, they allow us to infer something about the noise behavior of our device. So if we run a bunch of these circuits and we measure some observable, like this A that I previously said, if we measure this observable on the output of these circuits, then we somehow can simultaneously know what we should get if there was no noise in the circuit, because we can compute this classically, and what we actually see on the device with the device's noise. And using this, we can infer some kind of map between the exact value that we should get and the noisy value. And what we can try to do then is invert this map to go from the noisy value to the exact value. And the hope is that the result of doing this for these classically simulable circuits, it is similar to what you would get if you were to do this inversion process for a circuit that we actually could not simulate classically, the one we actually wanted to run. And again, this is just kind of a hypothesis that one needs to test, but it turns out that, in fact, this is often the case, and that if the circuits that we were running for this sort of training step are a similar sort of structure to the one that we actually wanted to run, then, and we could not simulate classically, then the error behavior on the sort of classically simulable circuits is kind of similar to that of the non-classically simulable circuits. So you are able to come up with a pretty decent map for inverting the errors. So sometimes this can enable you to go from something that would have been a sort of very low accuracy result to a result which is actually very high accuracy. Okay. A sort of somewhat related idea is what I've called readout noise inversion here, though it has sort of different names. And the idea is that in some quantum architectures, like superconducting qubits, in fact, errors when we read out the qubits at the end of the circuit are quite significant. Like maybe you have like a 5% probability of getting the wrong answer when you measure a qubit at the end of the circuit. And this can really mess things up in your sort of final measurement results. But one way we can try to handle this is by learning what the map is at the end, what this sort of readout noise map is that we see, like what the probability is of going from 0 to 1 and from 1 to 0, and then basically inverting this map just by doing a sort of matrix transformation on the result in order to basically undo this measurement error at the end. So this sort of obviously relies on actually being able to characterize the readout noise pretty well, but this can be possible, and you can, again, get fairly good answers. Another important point there, I guess, is that the level of efficiency of this method sort of depends on how much correlation there is between noise of different qubits, because if you have to characterize the measurement noise for like n qubits at once, then this should take you time like exponential in n even to write down this matrix. But there's ways that you can try to sort of handle these correlations in the measurement errors. Something that Barbara already mentioned briefly is so-called dynamical decoupling. And here what we do is we add some carefully chosen sequences of gates in our circuit. And these generally should be single qubit gates because these are the ones which are sort of more accurate, they're easier to do. And they're designed to cancel out some kind of errors that we imagine as coming perhaps from interaction between the system and some sort of bath. So, for example, if you stick in a pair of X gates in your circuit, then this means that if you have some kind of Z error that sort of develops over the course of the circuit, then these X gates effectively cancel out that error and it sort of disappears. That's a sort of simple example of this. There's sort of more complicated things you could do as well. And again, this works well in practice. And finally, a sort of nice strategy is to basically postulate, so to throw away measurement outcomes at the end of the circuit which you know should not have been achieved. Like if you know that your quantum circuit should respect some kind of symmetry of the problem you're trying to solve, then this means that if you get an answer that does not respect that symmetry, then you know that something's gone wrong and you can throw that away. Like, for example, if you have some quantum simulation problem where you know that the number of electrons should be preserved throughout the circuit, if you get the wrong number of electrons at the end, then you know you can discard that result. So this can be very effective, but involves some level of overhead as well. Okay, there's a lot of other techniques as well. And another interesting thing about the VQE approach I should mention is that this may actually experience some inherent level of noise tolerance. Because in VQE, we're changing the parameters of the gates sort of smoothly, like we have a lot of freedom in what we do. And it may be that sometimes we can sort of cancel out the errors on the gates by changing our VQE parameters. So this should be especially the case for these sort of hardware efficient ansatz where we're sort of changing the parameters of the gates sort of in a very general way and at sort of quite a low level, quite close to the hardware. So this may enable us to sort of correct for some systematic errors perhaps in the gates that we have in our circuit. Okay, so I just want to summarize this sort of near-term part and then I'll go on to some longer-term algorithms. But just to summarize this part, so at least in my opinion, it feels that variational quantum algorithms are a really intriguing way to try to push what we can do with near-term quantum hardware. They're somehow trying to make maximal use of this very limited hardware that we have available to us. There's a lot of really interesting work that's been done in this area, but I think there's still a lot more that needs to be done to try to really validate that these algorithms are going to be useful and the best way to run things on this hardware. And I just want to highlight a few interesting directions that maybe some people in the audience could try to resolve. So I think maybe the first one, perhaps one of the most important, is it'd be really good to find some more convincing evidence that QAOA and similar algorithms to this are really going to outperform classical algorithms. So as we discussed yesterday, I think a sort of interesting direction for this is perhaps looking at constraint satisfaction problems rather than optimization problems. We've done some work on this, but I think there's a lot more to be done. And a particular direction of this is to even find better theoretical justification for how well this algorithm performs and how well other variational algorithms perform. To make the algorithms perform as well as they can, we need to develop better classical optimizers, perhaps ones that are very tailored to the particular problems we're looking at, or maybe we even just need to understand better what the best existing optimizers are for these problems. There are some barriers that I mentioned to variational algorithms working. It would be great to evade these barriers, obviously. And we need to develop new error mitigation schemes. And I think the last point I want to mention is maybe a provocative one, but I think, in a way, the most exciting thing for the whole field of variational algorithms would be if we can obsolete it entirely and say, okay, well, let's not sort of give up on the idea of developing algorithms that actually solve the problem we want to solve directly, and let's sort of, rather than getting the computer to optimize over these angles and the parameters of the circuit, let's actually find the algorithms ourselves and be able to solve the problems rigorously, perhaps, without needing to have this sort of numerical optimization step in there. So I think this would be very nice as well. Okay, so as I'm going to move on to a different topic in a second, maybe I should take any questions about this part or error mitigation now, if anyone has any.
I just wanted to ask about this matrix inversion.
Mm-hmm.
So are we basically compensating for the lack of quantum ability by doing sort of using classical power? I mean, in this case, are we kind of losing any advantage that the quantum is giving us because we have to do a huge amount of classical post-processing to kind of counter the noise?
Right, that's a great question. So an important point about essentially all of these, well, most of these methods that I mentioned is that they are efficient to do classically, but often there's some sort of scaling sort of going on there somewhere. So for example, like post-selection, if your probability of success is very low, then that means you need many runs to be able to actually see any successes. And this sort of noise inversion stuff, this is efficient if you're sort of doing it at a sort of local level, but if you're doing it at a global level, it becomes inefficient. And yeah, and I think most of these error mitigation techniques have a sort of similar flavor, that you can, do something that's sort of small scale, which is efficient, but if you try and do it something really big, then it becomes harder. So yeah, I think there is an important trade-off there. I mean, one important point to mention is that in many cases, we have a quantum algorithm that achieves an exponential speed up, or at least we think it does. So it's not necessarily a terrible thing if we pay an exponential penalty in terms of the error correction, error mitigation overhead, as long as the exponential is smaller than the exponential speed up that we had. So it's a sort of finely balanced question, I think. Okay, so I guess I'll move on to the sort of second part. Try and get this up. Okay, so in the next part, I want to talk about longer-term algorithms for combinatorial optimization on quantum computers. So yesterday, I advertised in the talk about near-term stuff, jobs at Spacecraft. So today, in the talk about long-term stuff, I have to advertise jobs at Bristol University. And I just want to mention that we're also looking for people there as well, and we're looking for postdoc level staff and also PhD students. So if anyone's interested in that, please feel free to discuss with me. Okay, and I sort of would like to mention some survey papers for this part of with this talk as well. Unfortunately, I'm not sure if there's a huge amount out there in terms of surveys of these sort of quantum algorithms for combinatorial problems. There is this brief survey paper I wrote a few years ago. It's kind of outdated now, but nevertheless, maybe that's a sort of interesting starting point for people. Yeah, and just to get started then. So today, the idea that we want to have in mind is that we're wanting to solve combinatorial optimization problems, right? So by this, I mean problems where we are trying to search over exponentially many solutions to some sort of to some problem, and we're looking for the best of those solutions. We're looking for the one that has the lowest cost or something like this. And we're imagining that this is a sort of discrete search space, so we're searching over strings of bits or something like that. So it's this sort of problem that sits naturally in, let's say, the world of computer science. And the kind of problems that we maybe should have in mind are things like coloring a graph, a collection of vertices and edges, with the minimum number of colors, such that no two adjacent vertices share a color. Or maybe finding the lowest cost route that visits all of a set of cities. So this is the famous traveling salesman problem, and I'll say more about both these problems later. Or maybe determining if some system of linear equations over integers is restricted to be in the set 0 and 1 has a solution. Something like that. And sometimes quantum computers can achieve some speed up over our best known classical algorithms for solving these kinds of problems. And these speed ups are sort of very interesting, and sometimes these are also provable speed ups in the sense that we can say, okay, if we have a particular classical algorithm like unstructured search, then there is a quantum algorithm like Grover search which provably achieves a reduction in the complexity, which sort of is a difference from, let's say, quantum algorithms for simulation or factoring or something where we don't have this kind of proof always. But the speed up that we get is usually a lot smaller. It's more of a sort of quadratic speed up. So the runtime of the quantum algorithm scales like the square root of the classical algorithm's runtime. Whereas, in these sort of quantum simulation problems, we often see an exponential reduction in complexity. So this is sort of, a bit of a trade-off there. And this is true for the algorithms I'm going to talk about today. They're all of this sort of quadratic or less sort of nature of a speed up. And the algorithms I want to talk about today, there's a few different ones. In fact, I'm in a slightly embarrassing position that several of them are my own work I want to talk about. But the first one I want to discuss briefly, because I know this was already discussed by Ronald the other day, is the use of Grover's algorithm for solving unstructured optimization problems, unstructured minimization, let's say. I want to talk about quantum algorithms for speeding up so-called backtracking and branch and bound algorithms classically. And these are a sort of very well-studied or sort of canonical almost approach for solving hard optimization problems sort of that go a bit beyond this sort of naive unstructured search approach. And I'd also like to talk about some results of Andrew Sambinus and co-authors on quantum speed-up of dynamic programming algorithms, which is another well-studied classical approach, and now we have some very nice quantum speed-ups for this too. And somehow, a feature of these algorithms is that even though they have these sort of provable improvements over some family of classical algorithms, the runtime is still exponential. If we have an exponentially hard search or optimization problem we want to solve, then the runtime of the quantum algorithm is still exponential. It just has a better runtime. And also, these algorithms require a sort of very deep quantum circuit. So they require many gates in sort of many layers of the quantum circuit. The circuit runs for a long time. So these, I would say, require a fault-tolerant quantum computer kind of by their sort of nature. And this leads to the kind of elephant in the room, which is like, how practical are these algorithms really going to be? And at the end, I'm going to discuss briefly how one can find some concrete bounds on the performance of these algorithms and how realistic they actually are. So that's sort of when you try plugging in some of these overheads for quantum error correction, which Barbara discussed, what do you see? Do you still see a speed up over classical algorithms or do you not? Okay, so just to get started, I'd like to briefly mention, again, how we can go from Grover's algorithm to unstructured optimization. So this is a very sort of hand-wavy and non-rigorous slide, but at least it should give a sense of how this algorithm works, I guess as a reminder for you. So imagine that we want to solve a problem which involves minimizing some function over the space of bit strings. So we imagine that we have some function f where we pass in a bit string of n bits, and we want to find the choice of bit string which gives us the minimal value of f, the one which x, such that f of x is smallest. Ronald pointed out to me that I think he did maximization during his talk the other day, so this is a totally different problem to that one, so hopefully it won't be boring. We want to use Grover's algorithm to do this more efficiently using a quantum computer. And the version of Grover that we're going to use is that if we run Grover's algorithm for unstructured search, trying to search for an element within a set of k so-called marked elements, marked bit strings z in a set of n-bit strings, then we can find such a marked element with order square root of 2 to the n divided by k expected uses of f. So, I guess I didn't say this here, but just to clarify, so we have a set of 2 to the n bit strings, all of length n, and we want to search for a marked bit string, so one such that the function f evaluates to 1. And we can do this with a complexity that looks like this, square root of 2 to the n divided by k. And this is a square root type speed up over what we would see classically. Okay, so how are we going to use this to solve optimization problems? So we've got this function f, which associates an integer, say, with each bit string, and we want to minimize this function f. And the way we're going to do this is have some sort of threshold, which I called t, and we're going to initialize this threshold by just evaluating the function somewhere, maybe in the all zero string, and we're going to try to use Grover's algorithm to find some x such that f of x is less than that threshold. So this is a value of an x such that the value of f is smaller than ones that we've seen before. And if we're successful, then we're going to update the threshold to the function value at that x that we just found. If we're not successful, then we stop and we output the last one that we found. Okay, so we're going to repeat this process until we hopefully find the minimum. Okay, and it turns out that the expected number of uses of this function f is about square root of 2 to the n. And why is this? Well, each use of Grover's algorithm, it turns out, gives us a random x that's smaller than this threshold t. So we run it. It not only gives us, if there exists such an element, something smaller than the threshold, not only does it give us one of these, it gives us a random one. Okay, and that means that the sort of update that we make to the threshold, so on average, it sort of kills off half of the remaining elements, right? Because we're picking something that's sort of in the middle of on average of those remaining elements. So this means that we can sort of calculate the complexity of each round of Grover's algorithm, and it goes like square root of 2 to the n divided by k, where k is the number of elements that are initially below the threshold, and then we get a sort of, k goes to k over 2, so we get like 2 over k in the complexity, then we keep on going, and eventually k gets to sort of 1, and we've only got one element left, which is the sort of the minimum one. And if you sum up this series, you end up getting like square root of 2 to the n, order square root of 2 to the n with some constant in the front. So, some of you will have spotted ways in which this is not rigorous, but this is at least the idea of how we can use Grover search like repeatedly to solve an optimization problem as well. So, and in fact, this is going to come up as a subroutine later in the talk as well. Okay, so this gives us a square root speed up for unstructured optimization. So this is just trying to find the minimum within some set without any knowledge of the set itself or about its structure. But classically, what we see is that often we can do much better than this sort of naive unstructured search by using the structure of the problem that we're looking at. So we might have some prior information about the way the problem looks, which means that we don't have to search over all of the possible solutions to find the best one. And two sort of general approaches for doing this classically are so-called backtracking and dynamic programming. So another way of thinking of backtracking is sort of trial and error. It's to sort of try something, and then if it doesn't work, you change it a little bit and try again. Okay, so a nice way to illustrate this backtracking algorithm, this backtracking approach, is via this graph coloring problem I mentioned. So this is an example of graph coloring. So we imagine that we've got some graph with vertices and edges, and we're wanting to color each of the vertices with, in this case, one of 3 colors. And we want to make sure that every 2 vertices that are connected don't have the same color. And hopefully I managed to achieve this with this graph, that we are able to color this thing with 3 colors. But it turns out that this is an NP-complete problem, graph coloring, and if you try solving it for arbitrary graphs with n vertices, the best algorithms that we have scale exponentially with n at their runtime. And this problem, as well as being sort of mathematically nice, also has a lot of direct applications in really practical tasks like assigning registers in some compiler, or maybe assigning frequencies in some wireless network, or scheduling, or something like this. You can sort of map some of these problems very directly to graph coloring, so it's really a fundamental problem in both theoretical and practical computer science. Okay, so how are we going to solve this graph coloring problem, right? So I'm going to describe a way of solving it, which is only a little bit less naive than just searching over all possible colorings. But it's an approach which, in fact, can speed things up quite a lot. So imagine that we have this very small and sort of simple graph, and we're wanting to color this thing with 3 colors. Okay, so how would we do this sort of naturally? Well, it's very natural that the first thing we're going to do is just pick one of the vertices and try to assign it a color. So let's choose this one in the bottom left, and let's consider different colors that we could assign this, okay? So we could assign this either red or yellow or blue. So let's imagine that we choose to assign it red. Okay, fine. So far there's no problem. We've just assigned one vertex the color red, and there's no difficulties with this at the moment. So, okay, let's look at the next vertex. Let's look at this one on the bottom right. And again, we can assign it red, yellow, or blue. These are the different possibilities. But we can already see that we should not assign it red, because that would conflict with the color that we've already used in the bottom left. So that means we've sort of already cut down the search space a bit. We can only assign it yellow or blue. So let's try assigning it yellow. And this seems to be fine. There's no problem so far. And so we're going to move on to the next vertex, which is the one in the top right. And this one, again, we can try red, yellow, or blue. But now red and yellow are both ruled out, because that will conflict with the colors that we've already got on the graph. So in fact, the only possibility we can assign this one is blue, which we can do. And now we're on to the very last vertex. And of our 3 possibilities, now again, there's only one which is actually a viable one, which is assigning it yellow. So that's what we do. And now we've assigned a valid coloring to all of the vertices in the graph. And the important point is that we can see, like looking at this tree of possible possible colorings that we've explored, that we've actually only explored a small fraction of it. So if we had explored every possible coloring, but this whole thing, this would be a sort of complete, like, ternary tree, and we'd have many more vertices that we've explored. So because we cut down the search space by sort of ruling out colorings which are bad earlier on, we've only explored a small fraction of it, which means that we've saved some time. And this is what the backtracking approach does. It sort of cuts off portions of the search tree where we know that this can't lead to a solution in order to make things quicker. Okay, so this is a sort of very general approach, and we can apply it classically whenever we have the ability to determine whether a partial solution is not going to lead to a full solution, if a partial solution is already ruling out some of the constraints that we have to satisfy. And we would like to speed this up with a quantum computer. So, okay, how are we going to do this? And what we're going to do is we're going to solve actually a more abstract problem, which I'm going to call like search within a tree. And here the idea is that we want to find some kind of marked vertex in a tree. And these are represented in this tree on this slide by these green vertices, which are the leaves. And we imagine that we can't just evaluate any entry in this tree sort of immediately. We can only sort of navigate around it using like local knowledge of the tree, right? So in particular, we don't know what the tree looks like in advance. We don't know which edges are present, which ones are not present. All we know to begin with is what the root vertex is of the tree, the yellow one here, and what the neighbors are of that vertex. So what we can do is we can sort of evaluate the root, and it tells us where its neighbors are. And then we can look at the neighbors, and we can evaluate those, and they tell us where the neighbors are of them, and also, whether their neighbors exist at all. And then we sort of can continue this process to explore the tree, sort of looking around it. And then, eventually we hope that we can find a marked vertex in the tree. So one which is one of these green vertices here. And like this is an abstraction of this sort of backtracking sort of algorithm that I described on the previous slide, because the idea is that each of the vertices corresponds to a partial solution to some constraint satisfaction problem. And querying a vertex to find out its neighbors tells us if we can sort of continue exploring down that potential part, part of the tree based on the partial solution that we have so far, or if there's no way to progress further, and in fact we should sort of give up and go back up the tree. So this tree that I had on this previous slide, I mean, this is just an example of this sort of abstract notion of having a sort of tree which we can query, and then we want to look for some leaf which actually is a sort of valid solution in the end. Okay, so classically, if we wanted to solve this abstract search problem in this tree, it's going to take us time that scales like order t, basically, if we imagine that there's just one marked vertex, one green one, then exploring the whole tree is going to take us time about t in order to find that in the worst case, or even on average. And we would like to speed up this tree search process quantumly. And it turns out that we actually can do this. There's a very nice algorithm of Alexander Belov's, and this can detect existence of a marked vertex in a tree that has t vertices and depth d using square root of td queries. Yes?
So the local knowledge that I have is like, below this vertex, there may be a green vertex, or there's definitely none. Is that, or what is my local knowledge?
No, okay, so I should be maybe a bit more precise. Okay, so we imagine that there are basically two oracles that we can query. One of them says, what are the neighbors of you? Like, where's the ones further down in the tree? You probably already know the one above, but what's the ones further down? And the second oracle says, are you a marked vertex? So you can sort of change the problem a little bit if you want and say, okay, maybe the leaves at a certain level, if you can sort of, if you want, you can get rid of one of these oracles by saying, okay, it's only the leaves that are marked, and that sort of expanding at a certain level says, okay, like if you have a neighbor, if you don't have a neighbor, that means you're not marked, or something like this. But sort of maybe the cleanest way is to say you have these two oracles, and you can find out the neighbors and say, okay, is it a good one or not? Yeah.
But graph coloring, I know more, right?
Sorry, for graph coloring.
Graph coloring, I know there may be a marked vertex, or there's definitely none. Like if red, then I know below this there's no solution. I don't have to continue.
Right, so the graph coloring problem has a little bit more structure, that's right, than the sort of abstract problem on the next slide. So for example, like with graph coloring, we know that this is a sort of ternary tree, which would be a complete ternary tree, but we've cut off some of the branches. So, and we know that the only marked ones are ones that are at a certain level. They're like at the bottom level of the tree. But in fact, these are not essential for the quantum algorithm to work. So yeah, it doesn't hurt you too much to abstract them away. Okay. Yes?
Is the worst case complexity still the same of this backtracking method versus the naive method of just checking like random bit strings?
Yeah, that's exactly right. So if we imagine that the depth of the tree is t, so basically imagine the tree is like a line that goes down like t levels, then the complexity is like scales like the number of vertices in that tree, which is in fact what you would expect. In fact, if we didn't have this, something would have gone wrong, because we can only explore the tree by querying to find out its neighbors. And if these neighbors are sort of in a sequential like order, then we can't parallelize this, right, using quantum parallelism or indeed classical parallelism. So we need to have some dependence on the sort of distance between the furthest away vertices in the tree, because otherwise we just couldn't get from one to the other.
And you also said that the backtracking algorithm will explore less of the search space somehow, but I guess even if you did the naive algorithm, you wouldn't expect to maybe check all of the cases. You'd probably expect to hit a solution before checking the whole space. So what's the kind of expected complexity comparison? Right,
so that's a great question. And in fact, so there's 2 points there. So firstly, the sort of naive unstructured search that's looking over all possible solutions, but maybe just querying at random, and then it will stop when it finds a solution. I mean, the expected runtime of that, like you only save like a factor of 2 or something over just the worst case, because if there's only one possible solution, which is not unreasonable for some constraint satisfaction problems, then you're not going to find it until you're sort of halfway through on average. But classical backtracking algorithms, like sometimes they might get kind of lucky, and based on some sort of prior knowledge about the search space maybe, happen to find the solution very early on, right? So they don't actually explore the whole possible backtracking tree, which, as I said, is like a subset of the whole tree, right, that we could possibly explore. And the quantum algorithm, well, the result of my paper, like, does not necessarily beat algorithms. It doesn't. Okay, the scaling of the algorithm is like the runtime of the whole backtracking tree, as opposed to the part of it explored by the classical backtracking algorithm, which could be less, right? But a subsequent paper by Andris and Kirkpatrick, they improved the algorithm to actually get a scaling that's like the square root of that time, the time that the classical algorithm takes to to explore the tree. So even in that case, you can still get a quantum speedup, though the algorithm is a little more complicated. Yeah, sorry, this is all a bit technical, but I mean, these are important points, so I think it's good to discuss them. Okay, so I'm not actually going to discuss this algorithm really at all. I mean, I know you'll be sort of hearing about quantum walks later on in the week, but I'm going to just mention that this algorithm of Belov's exists, and it's based on the use of a quantum walk within this tree structure. So classically, a way that you could solve this problem of finding a marked vertex in a tree is by doing a random walk through the tree. So you start at the root and you sort of toss a coin, like, do I go down to the left or right? And you sort of continue this process and sort of walk around the tree until you find, hopefully, a marked vertex. And it turns out that using a quantum walk, you can get basically a square root reduction in the runtime for this approach. And this is a very, very nice algorithm. Like I say, I won't discuss it further. And this algorithm is working in this sort of abstract setting where we have these oracles at each vertex that we can query to find out what to do next. But it turns out that you can indeed sort of turn this into a concrete algorithm based on these classical backtracking algorithms. And if we think about what these algorithms are doing, well, they're exploring a tree, which, if you have n variables, it has depth n. Like each time you go down a level in the tree, you're sort of assigning a new variable a value. So the number of variables tells you what the depth of the tree is. And the size of the tree, we don't know what it is in general in advance. We would normally expect it's exponential in n. So normally, these problems that we're solving, these constraint satisfaction problems, they're sort of inherently very hard. So we expect that the backtracking algorithm's complexity will scale exponentially with the number of variables. So we expect t to be exponential in n. But we hope that it's sort of better than the complexity of sort of totally naive unstructured search, which would be sort of the number of values each variable could take to the power of n. So like with the 3-coloring example, the complexity of unstructured search would be 3 to the n. And we hope that this t is sort of better than that. Okay, so if we apply this quantum walk algorithm for search within this tree to this backtracking tree, and you sort of do a bit of work to convince yourself that some elements of this process are efficient, and there's some sort of technicalities to deal with. But it turns out that there is a quantum algorithm corresponding to this classical one, which gives you a solution to this constraint satisfaction problem, or outputs that one doesn't exist, in time that scales like the square root of the size of the tree t, up to some lower order terms, which are like polynomial terms in n. So I think it's like n to the 3/2 log n or something like this. And it has a small probability of failure. So if we imagine that t is exponential in n, then this is pretty much a square root type speedup, a quadratic speedup. Okay. And I already mentioned that Andres and Kirkpatrick had a nice improvement to this algorithm in terms of understanding how much of a speed up we can get in terms of what the classical algorithm's actual runtime is, the actual part of the tree that it explores. Jarrett and Wen also had a nice paper in finding some improvements to the complexity as well in certain regimes, at least. And, oh yes, sorry, question.
You said on the slides that this quantum walk only detects whether there is a marked element, but doesn't find it, and how do you overcome it?
Great, so that's a great question. That's something I swept under the rug, and that comes into this poly n part of the complexity, actually. So, okay, so if you can, okay, so this algorithm detects existence of a marked vertex. In fact, I mean, subsequent to this, there's been some work on using quantum walks to find marked vertices, and it's possible you could sort of obsolete what I'm about to say using that, so I haven't thought about it. But yeah, this algorithm only detects, and to go from that to finding, you can, for this particular problem to do with backtracking, you can solve it by saying, okay, if I can detect existence of a marked vertex in each subtree, like let's say we started out at the root, and let's say I say, okay, is there a marked vertex in the left tree? And is there a marked vertex in the right tree? Then, if you get an answer yes, then you go down into that subtree, and then you can keep sort of recursing until you get down to the root, and that tells you the location of this. But this gives you some cost, and that cost is going to be like a factor of n, because you are repeating this like n times. And so yeah, you do have some sort of overhead for that. And it may actually be these subsequent algorithms on search by quantum walk may be able to reduce that overhead a bit. I'm not sure. Yeah. Okay, and we now have this quantum algorithm for backtracking, which solves constraint satisfaction problems. But a more general thing is to try to solve optimization problems, so problems where we're trying to find the best possible solution. And one way that a fairly similar idea can be applied in this setting is a classical procedure called branch and bound. And the idea is that, again, that we have some kind of tree-like structure, but it's somehow a more informative tree structure because we still have some kind of branching procedure, some way of sort of going down in the tree, but we now have something which, rather than just saying that whether a vertex is sort of allowed or not, if it leads to a possible solution, we have something which is a sort of bounding procedure. And what this does is it gives us a lower bound on the cost of any solution that corresponds to exploring that branch of the tree, right? So, okay, maybe it's easiest to sort of explain this with this sort of abstract example here. So we imagine that each vertex in this tree corresponds to a subset of the possible inputs. And we imagine that each input has a cost, like each potential sort of solution to this problem has a kind of cost. And we have a procedure where for a given subset of solutions, it tells us a lower bound of that cost. So we might imagine, for example, that we have some sort of heuristic, which is a sort of relaxation of the problem that we're wanting to solve, that is easy to run, and it tells us, okay, this is not necessarily the best cost of any solution in this subset, but there's at least a lower bound of this cost. And sometimes you can do this. So, for example, integer programming is a hard is an NP-complete problem, which is very hard to solve. But linear programming has a polynomial time algorithm. So any solution to a linear program on with a sort of certain set of variables gives you a bound on the quality of a solution that you would get if you solved the sort of corresponding integer programming problem, right? So sometimes we have efficiently runnable algorithms which can indeed give us bounds on the cost of a solution. So, okay, so we imagine that the root sort of corresponds to the set of all potential solutions, and then we have some algorithm we run on the root, and it says, okay, the lower bound of the cost of everything in this set, so that's all of the possible solutions, is 1. And then we look at the sort of subsets, like we imagine we split into 2 subsets here, like a left half and a right half. And our sort of heuristic says, okay, a lower bound of the cost of everything in this subset is 1, whereas a lower bound of the cost of everything in this subset is 3. And we can use this heuristic for various different subsets, like we can split this left-hand one into 2 parts, and then we can split into 2 parts again, and so on. And the sort of point, the reason why this might be useful is if we imagine that we've explored part of this tree already, like, okay, I'm not sure if I have let's see if I find a good example here. Okay, so let's say we've already explored this part of the tree, and we've already seen that we've got a solution with cost 4 here. So the leaves correspond to the actual, bit strings, the actual things which are potential solutions to the problem, as opposed to subsets. So these are like subsets of size 1. Imagine we've already found a solution with cost 4. Then imagine that we've gone down this branch of the tree here on the right-hand side, and we've seen that everything down here in the bottom right has cost at least 5. Well, there's no point in exploring this part of the tree at all because we've already found a solution with cost 4, and nothing in this part of the tree can be better than that because it has cost 5 at least. And it turns out this 5 is just a lower bound because there are solutions with cost 6 and cost 8 down there. But we know that we don't even need to look at them because we can't do better than the one we already found. So, okay, so what we see with this sort of bounding procedure, this kind of cost function, is that the costs that it reports, they can only sort of increase as we go down the tree. They can't decrease. And the idea is that we're going to use both of these procedures to try to, again, get a faster algorithm for exploring the tree. Okay, and a sort of hand-wavy version of the result that we get here is that if there's a classical algorithm that solves some optimization problem using these branch and bound procedures t times for some t. Then there's a quantum algorithm solving the same problem, same same optimization problem, using these branch and bound procedures square root of t times up to some lower order terms, which I think are lower order in t and like also in the number of variables. So it's like poly n times by I think like log factors in t. So this is a similar sort of near quadratic speedup, and this is basically a purely classical procedure that uses this quantum algorithm for backtracking as a subroutine. So I don't want to go into details about it, but just to sort of get the flavor of how this would work, basically to turn this sort of optimization problem into a sort of search or like constraint satisfaction kind of problem, we could say, okay, let's write down some kind of threshold function in a similar way to what we did for unstructured search and optimization, where we say that a solution satisfies the function if its value is below a sort of certain threshold, right? So, for example, our function might be, we're only going to consider potential solutions that have a cost 4 or lower, for example. And then if we were to use this as our sort of thresholding function, then this would throw away some parts of the tree, like it would throw away this ones with like infinity cost, cost 7, cost infinity, cost 6, 6, 8, 5. So it would only leave us with sort of part of this tree. And this would be the part of the tree that we would explore with this tree search or sort of backtracking approach to try to find something that actually does have costs below that. So really the sort of technical details of the algorithm are in choosing this sort of threshold in order that we can apply this algorithm efficiently. And it turns out that you can have a procedure where you choose it such that it's sort of, you end up with exploring a sequence of trees which grow in size sort of exponentially, but depending on what the threshold is you choose, in such a way that you never end up exploring much more of the tree than the best classical algorithm would explore. So somehow the best threshold we could pick in this tree would be 4, because any threshold that's lower than that would sort of throw away the best solution, and thresholds higher than that might include some other potential solutions which are not the best one. And so somehow the goal of the algorithm is to choose a threshold that's close to that best possible one. And it turns out that you can do this, and this gives you an algorithm which, up to some sort of lower order terms, gets this sort of square root type improvement. So for those here who are physicists, one application you might find nice is that you can use this to find ground states of the Ising model, and this is defined in terms of some variables z that are plus minus 1, and some constants aij, and we want to find some assignment to these z's such that we minimize this energy here. And this, again, turns out to be a hard problem, like an NP-complete problem. And in a particular case, generally, you can sort of convert this branch and bound, you can convert finding these choices of z's to minimize this energy into something which fits nicely within this sort of branch and bound setting. You can write down some approach where, based on some choices you've already made to assign plus or minus 1s to some of these z's, then you can sort of write down a bound on how good a solution you could possibly get based on what you assigned to the other z's that you have not yet thought about. And you can use this to throw away some parts of the sort of search space. And a nice case where you can apply this and actually analyze the complexity is this so-called Charrington-Kirkpatrick model. And here we imagine that these coefficients aij are actually picked at random, like they are picked maybe from a normal distribution. And then it turns out that, firstly, the energy itself is known, like there's some beautiful results which precisely characterize what this energy is. And in fact, I think this is something that Parisi recently won the Nobel Prize for, actually, the heuristic argument for this, which was then later sort of rigorously proven by Talleyrand. So I think there's even a sort of Nobel Prize that goes into this result, not my result. And I think I can say with some confidence. Yeah, so it turns out that with this particular model, based on the properties of of this distribution, you can work out how often you throw things away, and you can calculate what the running time is of this algorithm. At least you can find some bounds on it. And it turns out that, at least based on the theoretical bounds, the runtime's like 2 to the 0.226 times by n, which interestingly is better than what you would get using Grover search, for example, which would be 2 to the n over 2. And numerically, I think, in fact, the runtime is even a bit better than this from what we can see. So this says that, at least in some cases, using this sort of backtracking type approach, you can do things which are sort of better than you would get if you were just using Grover's algorithm in a sort of straightforward way.
Can I ask a question?
Oh yeah, sure.
This runtime, this must be then some average case runtime.
Yes, that's right. Yes, so that's quite right. So this is okay. Yeah. So this is indeed, I think, the expected runtime of the quantum algorithm over instances. I mean, there's very good concentration actually. So there's almost all of the time you're going to get runtime that's like this. But you're right, indeed. This is not a worst case bound. Yeah. Okay. So.
Can I
Yes.
ask a question just before we move?
Oh yes, sorry.
Sorry.
Yeah.
How do we actually create the subsets in the first place such that the cost goes increasing as we go down the depth? Because we don't know what the costs are in the first place, but we are saying we are able to create a subset in such a way.
Right. Okay. So this is something that is sort of depends on the problem that you're looking at, right? So, for example, like in this Ising model case, like what you can do is you can say, okay, like imagine that I want to compute this quantity on the right-hand side, which is a sum over pairs I and j of some constant times by zi zj, okay? And imagine that I've already assigned some of these zi's some values, like plus or minus 1. Then, so we have a set of variables that have been assigned values and a set of variables that have not yet been assigned values. So then you can split up this sum in terms of, pairs that are both within the set that have been assigned values, in which case we know what that part evaluates to. Part which is pairs that have neither been assigned values yet, we don't know what that is, and a part which, one has been assigned a value and the other one has not been assigned a value. And these second two parts, although we don't know what the answer is yet, because we haven't assigned values yet, as you say, we would have to search over this space. We can put some bounds, like using some sort of Cauchy-Schwarz inequality or something like this, on how well we could do with any possible assignment to those variables, right? So we can say, like, for example, if the cost is already very high based on just the first few variables that we've assigned, like if the energy is very high, then we're not going to be able to sort of correct that by whatever we assign to the variables later on. And, you have to do the analysis to see if this is actually useful, but it turns out that this does give you sort of a non-trivial reduction in the space that you have to explore. But for some other problems, it may not be obvious how to find such a sort of heuristic that tells you, okay, the cost of anything that starts from this point is going to be bounded by something. So, yeah.
So I don't know the result myself, but instead of Cauchy-Schwarz, it's just got to be a Hölder inequality, which is another occasion for you to practice your German and the umlauts.
Well, this is why I didn't dare to say it. No, sorry. No, that's true. I think you're right. Actually, yes, it is a Hölder inequality. I said it quietly. Yeah. Okay. Yeah. Okay. So. There are some other applications of this sort of approach to, for example, cryptography. Like it turns out that lattice-based crypto systems, one way of attacking them classically and now also quantumly as well is based around this notion of backtracking and sort of basically trying to find a short vector in a lattice is the underlying computational problem that you need to solve here. And it turns out that something similar where you sort of throw away partial solutions that don't seem to be going anywhere is also useful here too. You can apply this problem to some variants of the traveling salesman problem, Boolean satisfiability problems, and so on. And people have also now implemented sort of small-scale numerical demonstrations of this algorithm, which is sort of nice to see as well. Okay, and so the next algorithmic approach I want to discuss, which is kind of quite different, I guess, is one called dynamic programming. And this is something which I guess those of you who are computer scientists in the audience will probably have been taught in your undergraduate degrees, but others may not have seen, where what we're imagining is that we have, again, a problem that can be sort of understood in terms of some sub-problems. And now what we're wanting to do is we're trying to solve the overall problem more efficiently by somehow storing the answers to these sub-problems and combining them together in order to get the overall solution. So we imagine that maybe we have some problem which has some kind of recursive structure where we can start out at the top and then we can sort of split the problem up in perhaps different ways, which may well overlap somehow these sub-problems. And we could get an exponential time algorithm by combining, by sort of solving this recursion and combining the answers at the end. But instead we sort of build up the solution from the bottom up and start out with like small partial solutions and sort of combine them together and to get a total solution. And it turns out, based on some work by Andres and co-authors, that we can accelerate some of these classical algorithms as well using quantum algorithms. And I just want to mention one example of this, which is this so-called traveling salesman problem. And just to define this for those who haven't seen it, we're given some graph that has n vertices and has some edges, and those edges have costs or weights associated with them. And we're looking for some kind of tour of all of the vertices in G that travels only by these sort of valid edges and has the minimum total cost. So the sort of intuition behind this is we imagine that we have some salesman who is traveling through n different cities, and he wants to visit all of them using the minimum total time, and he wants to get back to where he started in the end. And this is something which, although in practice it may not be that hard, in fact for realistic road networks, people have solved very large-scale problems, traveling salesman problems by now. Even though it may not be so hard sort of in practice, theoretically this is still a sort of exponentially hard, like it's an NP hard problem, and it's interesting to try to find efficient algorithms for it. Okay, so one thing we could do is try every different possible path in turn, every different sort of possible choice of these vertices in order. And there are n factorial of those. This is all possible permutations of the vertices. And we could use Grover's algorithm to search over those to find the minimum cost tour going from beginning to the end and sort of back again. And this would give us a square root of n factorial sort of complexity. But it turns out that, in fact, there's a classical algorithm that runs in time 2 to the n, like up to some lower order terms. So this is much better than n factorial, and it's also much better than square root of n factorial. So the quantum algorithm doesn't actually even compete with this known classical algorithm at this point. But it turns out one can find a quantum algorithm which does outperform this 2 to the n classical complexity. And this is based on a different way of understanding, well, a particular way, I guess I would say, of understanding the traveling salesman problem, which I just wanted to describe briefly. So we're going to define some sort of auxiliary function f, which takes a subset and 2 vertices, and it's supposed to be the length of the shortest path in the graph corresponding to the subset of vertices S, that starts at vertex u, finishes at vertex v, and then visits all vertices in S exactly once, right? So we imagine that, I guess u and v are sort of in S, and we want to find some path that goes everywhere within S, starts out with u and finishes with v. And we want to find the shortest such path, right? Okay, so we can see that, okay, first point is if we let S be all of the vertices in the graph, and we looked over sort of all pairs, and we looked for this thing where u is equal to v, then this would be actually the problem that we want to solve in the first place. This would be the traveling salesman problem. So if we could compute this for this particular subset and for all u, then we can solve this problem. And okay, so this thing then has a sort of nice sort of recursive structure that we can write down, which is that, and I'm sort of just going to index this by this sort of diamond symbol over here, that this function is the minimum over all vertices that are neighbors of U and are in the set S and are not equal to the vertex V, of the cost of getting from U to T, to this neighboring vertex, plus this same function F, looking at all vertices in S where we take away the vertex U that we've now already dealt with. So this is saying, okay, like, look over all different possibilities for the first vertex that we move to from S, and then solve the problem once we've fixed that, that vertex, right? So this is saying, okay, let's sort of recursively consider different ways that we can move from U. Okay, so maybe that's at least sort of plausible. And classically, this is a way in which you can get this 2 to the n complexity for solving this problem, because we can consider all subsets S, and there are 2 to the n of them, all different possible subsets of vertices S. There are 2 to the n of them, and we can look at them starting from the smallest ones, the ones with maybe one vertex in them. Then we can look at sets with 2 vertices in them and 3 vertices and so on. And each such set, we can compute this quantity here, this minimum, using the values of F that we've already computed for the smaller subsets. Right? So somehow this minimization is not too hard to do. This takes like polynomial time. There's only n, or at most, like I guess, n minus 2 or something, different choices T that we can have here. The sort of costly part of computing this is the fact that this F sort of goes down like recursively. And if we already know what this value of F is, then we can compute this with very low cost, this minimization. So this gives us a sort of roughly 2 to the n time classical algorithm. And to speed this up quantumly, it turns out we actually want to use a different recurrence, which is in a way sort of generalizing this previous one, where we, instead of minimizing over all choices of T that are adjacent to U, we're now minimizing over all subsets of the set S of vertices we're looking at that are of a certain size, some K. And so we're choosing a set of vertices X such that U is in X and V is not in X. And then we are minimizing over all vertices in X that are different from U of the cost of getting from U to T in the subset X, plus the cost of getting from T to V in the subset of S, taking away the subset S, and adding in the vertex T, right? So this is basically saying, okay, we're looking over all subsets of the cost of getting from, and all vertices within that subset, of a cost of getting from U to T within that subset, and then the cost of getting from T to V. And this may take a little bit more convincing to yourself that this is the same thing, but indeed it is the same thing. And at least unless I made a mistake in writing it down. So, okay, so we can do this. And this is useful because we can then write down a quantum algorithm that looks like this. We're firstly going to calculate this function F for all small subsets classically. So all subsets that are size at most n over 4 up to some small 1 minus alpha sort of scaling coefficient comes in front, and this alpha is a parameter that gets chosen later on to optimize the algorithm. So we can calculate this quantity F for all of these subsets classically using the dynamic programming algorithm that I previously mentioned. So the cost of this is going to be basically the number of subsets that are of this size. And then we use this Grover-based quantum minimum finding routine to compute this particular sort of minimization quantity here, right? So this sort of looks a lot like the second one on the previous slide, but this is basically the quantity that we want to compute in the end, like the cost of the sort of minimum. The minimum sort of path from this. This is like minimizing over all subsets S of the cost of going from, yes, okay, so this is minimum over all subsets S of a certain size, and minimizing over all pairs of vertices in that subset of the cost of going from the first vertex in that pair to the second one within that subset, and then the cost of going from that second vertex in the set back to the first one, right? So, okay, this is another one which may not be totally obvious, but it is the same thing. And how are we going to use quantum minimum finding in this way? Well, we can look at the different sort of subsets where we need to actually compute these values. And it turns out that if we look at the recurrence on the previous slide, the different values of the choices of the size of S that we need to use are either n over 2, which is sort of what which are and they're initially n over 2, right? This is what we have in this recurrence here, and to compute these values, we use a quantum minimum finding based on the previous recurrence here, the one at the bottom. So we use quantum minimum finding sort of within this, and we have a choice of k to make within that recurrence, and we choose it to be like n over 4. And then this gives us like a next level down of this recurrence. And now we end up computing this quantity f for subsets S that are of size either alpha n over 4 or 1 minus alpha times by n over 4. And in these cases, in these cases, we can use the results of the classical preprocessing that we did using dynamic programming. So what we end up with is that the overall complexity of the algorithm is the complexity of the initial cost of doing the classical dynamic programming step, which I've sort of denoted by this thing here. So this is the notation for the number of subsets that are size at most 1 minus alpha times by n over 4. And so that's the sort of initial classical step. And the quantum minimum finding step turns out to look like this. So why is this? It's because we're searching over n over 2, choose n over 2 subsets S that are size at most n over 2. That's sort of in the first level of this recurrence. And then within the next level, we're searching over n over 2 choose n over 4, and then we get n over 4 choose alpha n over 4, which is sort of the third level of the recurrence. And each case we're using quantum minimum finding, so we get a square root on top of those complexities. And it turns out if we choose alpha carefully, then we can end up with a complexity of 2 to the 0.79 times by n, which is better than this 2 to the n complexity. And even if we do a sort of simpler algorithm where we don't have this sort of third level of the recurrence and we just choose alpha equal to 0, then we can get a complexity of 2 to the 0.81n, so this is a little bit worse only. Okay, so this is a little bit technical, but I sort of wanted to show you it just to indicate how you can use these fairly simple quantum subroutines in a sort of more interesting way within a more complicated algorithm to see an improvement over some non-trivial classical algorithm. Okay, so last point I wanted to discuss is, will all of these quadratic type speed-up quantum algorithms actually give us some sort of real-world speed-up in practice? Because these speed-ups are indeed, they're only quadratic, they're not exponential, and quantum hardware is pretty limited in the sense that sometimes the clock speed is slow of quantum hardware, and also we might have really big overheads from fault tolerance. So when we put these things together, do we actually see a real-world advantage over classical algorithms? And I just want to sort of talk about how one can do a calculation to determine if there is a chance of this. And this is something that we did a few years ago, where we picked a particular problem, in fact, the graph coloring one. We tried to sort of write down the quantum circuits associated with this algorithm and really tried to optimize the performance of these quantum circuits. So, try to look at all of the different steps in the algorithm and figure out how to really sort of push down their complexity as much as possible, often using previously developed subroutines where people had also tried to really find the best possible quantum circuits. We then tried to estimate what the running time of these algorithms was going to be, right? And this is a sort of interesting challenge because the sorts of problems that we want to apply quantum algorithms to, by definition, are ones that are too hard to solve classically, right? So in order to compare the quantum algorithm to some classical algorithm, like how are we going to do this? Because if we want to get an estimate for the classical algorithm's running time, then by definition it's going to take too long to do this ourselves. So we have to come up with some way of extrapolating from the performance of smaller instances which we can solve to the likely performance of larger instances which we can't solve yet. And the way that we did this is we tried to choose a sort of family of random instances. So in the case of graph coloring, it's kind of natural to pick families of random graphs. And we tried to sort of use some classical algorithms for small-sized random graphs, which we can run, and see what the scaling of the complexity looks like, and see how this is going to hopefully increase when we have larger sizes, so that we can figure out, okay, how big is the quantum speedup likely to be, or is there indeed going to be a quantum speedup? And then the sort of final step, I guess, is to work out what's the actual running time of the quantum algorithm going to be. Like once we plug in some real numbers about the time it takes to execute the gates and what the overheads are, and how much error correction costs for various different possible hardware parameters, because we don't know how good the hardware is going to be in a few years' time, so we have to sort of guess. Okay, oh yes, and I guess, the last point is that we should, when we're doing all these calculations, really compare the quantum algorithm against like what is a good classical algorithm. So rather than picking some classical algorithm which is not a sort of fair competitor, one which is not very good or is like known to be suboptimal, we should at least make some effort to choose a classical algorithm which performs well. And that's what we tried to do. And we compared against this classical graph coloring algorithm called DSATO, which I think is considered to be a pretty good one. Okay, so then how do we actually work out the running time and the space usage of the quantum algorithms? So we used a sort of fairly simplistic method, and certainly one could do much more detailed analyses. But what we did in this particular work was to use the surface code, which Barbara's discussed a lot, and we used a sort of particular variant of the surface code, which is a surface code-based computation, which I think may not be now the sort of the most efficient one, but anyway, like one based around magic state distillation and sort of factories and so on, which we inject magic states into a circuit. And we wanted to find, we used a variant of this model which was sort of optimized for speed at the expense of space. So the result of these sort of calculations will be sort of very high space usage, but the time usage is sort of compressed down as far as we could. Okay, and then we had to somehow convert the complexities that we obtain into real-world running times, and we had to sort of put a finger in the air and sort of guess what the complexities of or what the performance of the quantum computer is likely to be in sort of various different regimes, and we came up with different regimes which we called realistic, plausible, and optimistic. And anyone in the audience who's an experimentalist may differ with some of these words on this slide, especially realistic and plausible. But in any case, the realistic ones I think are all results that have been reported in the literature, possibly not all in the same experiment, but they've all been reported in the literature. And then we said, okay, let's estimate that we might have some order of magnitude improvements on these. Okay, so realistic is supposed to be what we can do now or near enough, and plausible is, let's say we work really hard and we get an order of magnitude improvement. Optimistic is, okay, let's say things go really well and we get 2 orders of magnitude. Okay, so there's some sort of good news and bad news. So in the most optimistic regime for hardware parameters, we can get speedups at least compared with one standard classical PC, this is circa a few years ago. And the sort of speedups that we see are of the order of 10,000 times or something like that, right? So this is for problems that can be done in one day. Yes, David.
So you also have a number of qubits that you...
Yeah, I'm going to show this in a second,
right.
Yes. Yes, this is the bad news.
But for your table, you also have a kind of a maximum number of logical qubits, right? Because otherwise, if there's a difference in scaling, then you can't summarize it by one constant factor, no?
Right. Okay, so this is a good point. So I should definitely clarify this, that we wanted to fix a total amount of time that we were allowing the computation to run for. So these are, as you say, these are sort of asymptotic separations. So if we allow the quantum computer to run for a year, then we're going to get a bigger speed up than if we allow it to run for 1 day. And we decided that it was reasonable to wait for a day for the answer, but we didn't want to wait for a year. So this speed up factor would increase if we're happy to wait for a week, but it would decrease if we only want to wait for 1 minute. Yeah. So this is an important point. And the speed up, unsurprisingly, gets much less if we're thinking about the sort of quantum hardware that we have available today. And there's an interesting point, which is that if we figure out a way of taking into account the cost of the classical error correction processing, then actually the speed up can disappear altogether, right? And I'll say a bit more about what this means in a second. And the number of physical qubits is very large as well, actually. Like it's like 10 to the 12, so this is like 1 teraqubit, I guess. And almost all of these qubits are used for fault tolerance. They're almost all these sort of magic state factories. And the sort of obvious point is that this strongly motivates the design of better fault tolerance techniques. So, but I think, yeah, I mean, one thing, even though these results end up being sort of pessimistic in terms of the overall complexity of the quantum computer you would need, at least one thing that is nice is somehow there's a clean separation between the cost of the fault tolerance and the cost of the algorithm, right? So at least we can say, okay, the algorithm has a hope of achieving a speed up, but to make it viable, we really need to reduce the cost of the fault tolerance part. Okay, so just to sort of summarize these things in a table, the sort of results that we get, and I won't go through all of these numbers, but the sort of results we get are that, the sort of, if we have a graph coloring problem on a random graph, when we want to solve it, in at most 1 day, let's focus on the optimistic regime. In the optimistic regime, we might be able to solve on a quantum computer a graph coloring problem on a graph of 144 vertices. The number of T-gates or Toffoli gates that we need is of the order of 10 to the 20. That's this number here. The number of qubits that we need, physical qubits, is of the order of 10 to the 12. And the sort of overall speed up over just one classical computer, so not over a supercomputer, this is over one classical computer, is of order of 10 to the 4. So this is obviously, as I say, making various assumptions about various parameters. And yeah, so this is better than no speed up, but clearly it's fairly daunting. And I should say there's some other work by a team by Yuval Sanders and co-authors, and they end up with actually more pessimistic results, looking at various other constraint satisfaction problems and various other algorithms. One reason why the results are more pessimistic is that they don't sort of have this sort of extreme notion of parallelism that we take in this work. They want to have just one of these magic state factories operating at any one time, so they have fewer qubits, I think, but their time complexities are higher. So they don't see, I think, any sort of speed up over classical computing. Okay, and I should just go into a bit more detail about this point of classical error correction processing. So as Barbara discussed, to do the error correction in our quantum algorithm, we need to have some classical processing to figure out how to translate the measurement results into the error correction step. We need to understand where the errors have actually occurred, and then we need to actually fix them. And this is something that costs some time. Like even this minimum weight perfect matching algorithm that Barbara mentioned, which is pretty efficient, we still take some time to run it, and we still need to optimize it. And basically, the concern one might have is that if we need a gigantic amount of classical processing for the error correction, then we might as well have just used that classical processing to run the algorithm in the first place, right? So if our 10 to the 12 qubits need 10 to the 12 classical CPUs to do the error correction, then we might as well have just used those classical CPUs to solve a graph coloring problem in time, like 10 to the 12 or something. So for a fair comparison, we should take this into account as well. And the way that we sort of tried to do this is say, okay, let's let's take the running time of an error correction algorithm, which people tried to optimize, quite hard, and they reported what the running time was of an error correction step. And let's try to extrapolate this to more sort of exotic hardware platforms, like maybe if you have a GPU, you can speed things up, or maybe you even have some special purpose hardware. And we had some guesses that, we can discuss about whether these are plausible. We had some guesses for what the speed up might be if we did this. And basically, we can, for different numbers of gates in the circuit, different numbers of Toffoli gates, we can look at what the amount of classical processing is we might need to implement these gates, to do the error correction associated with these gates. And now we have, again, different regimes, but now there's a slight difference to the previous slide in that we're now in the optimistic regime looking at having better classical hardware. So this would be like, having some special purpose classical hardware maybe that can implement the error correction much more efficiently. And it sort of turns out that, the number of processor days that we need to implement error correction for different numbers of gates in these different regimes is pretty daunting as well. So it might be like of the order of 3 times 10 to the 8, 3 times 10 to the 8 gates for processor days, for example, if we need to do 10 to the 20 Toffoli gates. And on the previous slide, we saw, okay, so we have of the order of 10 to the 20 gates, perhaps, in the circuits we want to run. So this means that maybe, the sort of most relevant one is this one in this bottom right-hand corner here. So this is basically saying that we should probably knock off a factor of 10 to the 8 from the speed up on the previous slide, which would actually make it worse than classical. So, so basically, I think, these are all very sort of hand-wavy numbers, but I guess the point of the slide is that we should sort of take into account the cost of this classical error correction as well. And so, okay, so I think, really the sort of take-home message perhaps is that it's not ruled out that we might be able to get a speed up for some combinatorial optimization problems, which are very common and are very practically relevant. I mean, we have some asymptotic speedups, and we might even be able to get a sort of real-world speedup of some kind. But really, there's a lot of challenges that we need to address to actually make these speedups happen. And in particular, on the fault tolerance side, this seems to be kind of critical to actually make these sorts of speedups a reality. So I don't know if people would take this as a sort of positive or negative point to end on, but in any case, this is the end. So thank you very much.